Good afternoon, professors, advisors, guests, and students, and thank you for attending our presentation. Over the course of this semester, my teammates and I have been working on the conceptual design of an offshore wind support vessel. In this presentation, we will describe our vessel and how we designed it. Before we begin, I would like to introduce myself and my teammates, along with our advisors and the outline of this presentation. Corbin Only is from Monterey, California, equipped with working experience from Herbert Engineering Corp. And Austell. Andrew Carafa is from Ada, Michigan, and has industry experience from Fincantieri Bay Shipbuilding with career plans in sustainability, particularly in offshore wind. Jack Jackson is from Carrollton, Texas. He worked at the American Bureau of Shipping and plans to go into marine classification. Malay Metz is from Berkeley, California. She plans to enter the large ship design and repair industry, making her experience at General Dynamics NASSCO particularly valuable. My name is Kyle Green, and I am from Queens, New York. I had the pleasure of working for Metal Shark Croatia this past winter and wish to go into small ship design. The EON design team also includes our mentors. We thank them for all their generous contributions to our decision-making. We would especially like to thank Phil Essex, Nolan Conway, and Lowell Dickerson for their extensive advice and shared experiences. The outline for today's presentation is as follows. We will introduce our design by the objectives and criteria provided to us. Then we will step through the elements of the ship design, explaining how we made the major design decisions. We will give an overview of the applicable statutory, classification, and international rules governing our design. And finally, we will present a few conclusions, and then we look forward to taking your questions. First, we will describe the objectives which our ship was designed to satisfy. The objective of this project was to learn the principles of ship design by producing the concept design of a service operation vessel, or SOV. Functional requirements are the requirements which directly pertain to the mission of the vessel. They are primarily to provide a maintenance platform for offshore wind platforms, to facilitate multimodal crew transportation, to accommodate offshore workers for cruises of up to 30 days, to transport various payloads for working on offshore wind platforms, and to enable offshore operations with heavy machinery. The non-functional requirements are not directly related to the mission, but are important components of how the ship operates. They include a high level of redundancy for continuous operation over long periods, a sharp reduction in the use of fossil fuels compared to similar vessels, mitigating pollution by ensuring that no oil-bearing tanks sit on a shell boundary, and compliance with applicable regulatory standards, as well as meeting requirements for classification with Bureau Veritas, BV. Performance requirements are specific numerical and technical requirements with no quote-unquote wiggle room. I will discuss our main technical requirements here. They're compliant with dynamic positioning 2. The ship's gross tonnage should not exceed 500 gross registered tons. It must be able to maintain service speed for 24 hours without burning fossil fuels, and there must be an overall 25% reduction in the use of fossil fuels compared to similar ships. By way of overview, these are our principal technical requirements and a comparison with how we did. Our draft requirement maximum was 6 meters, and our ship currently draws 5.83 meters in the full load departure condition. The speed profile we were provided is shown here, and we have the powering to meet these demands as stated. The ship requires the capability of a 30-day cruise and range of 5,000 nautical miles. At this stage in design, we project even greater capability. Finally, the complement, including officers, unlicensed crew, offshore workers, and hotel staff, was given as 60. As is, we have capacity for 60 persons, but one of our mentors proposed that this number could be further expanded with FEU modular cabins placed on the deck. We do have the electrical capability to support this expansion if needed. Next, I'll pass it off to Corbin to discuss the design engineering of this project.
Thank you, Kyle. Now we're going to go through each aspect of the vessel and discuss how we reached the current design. I'll start off with the hull form. The hull form we designed was based on the apparent hull in the form of the MMA Pride, another offshore support vessel in a similar sector. It was then combined with a baseline hull generated using Orca 3D. The major difference between the baseline hull generated and the parent hull was the depth of the aft section, which was far deeper on the MMA Pride. We decided that we wanted to emulate this on our design to give more space for machinery and tankage in the aft end of the vessel. The only other major departure we made from the parent hull was making the bow narrower. This gave a significant reduction in resistance for very little cost, since there is no major systems in the forward end of the vessel. Here you can see the lines plan for our vessel. Overall, the hull is not a major departure from similar vessels, making it a proven design that can easily be produced in many shipyards. Here you can see the principal characteristics of the hull. These parameters were derived from parametric analysis first and then adjusted based on our specific mission systems and needs. Now we can move into the general arrangement of the vessel, starting with the centerline profile. Overall, the arrangement seeks to maximize crew comfort by separating any berthing from machinery as much as possible. On the current design, there are at least 2 decks of separation between any major machinery and any berthing, with most being at least 3 decks away. Here's the main deck of the vessel. The main deck contains both the cargo spaces as well as the mission equipment, including the crane, walk-to-work system, and daughter craft. A stepless landing was also included for easy loading of passengers and workers from other vessels onto ours. These mission systems will be elaborated on in more detail later in the presentation. For easy access, the conference rooms, changing rooms, and client office were also placed on the main deck superstructure. The engineering spaces are the bottom 2 decks of the vessel. Besides all the necessary machinery, most of the space here is taken up by tankage. The only notable tank is the mud tank at the aft end of the vessel, which is meant to allow this vessel to operate in sectors beyond offshore wind in case that industry takes a downturn. There's also a large workshop space included on this deck for both onboard maintenance and maintenance of offshore wind cargoes. The accommodation spaces are located above the main deck. The overall layout is circular in nature to allow for exemption from tonnage measurement through tonnage openings. The accommodations were chosen in accordance with industry standards. This includes a single laundry space as well as the combined crew and officer mess. One unique feature is the inclusion of a basketball court on the lower forecastle deck for crew recreation. Since we had the space available, we thought that this use of space for the well-being of the crew was a slam dunk. The wheelhouse and helipad are on the uppermost decks of the vessel. The helideck is located as high as practical for easy landing of a helicopter. An additional firefighting locker is also included on this deck to meet helicopter safety standards. Additionally, since the vessel needs to maintain dynamic stability, the operator needs to be able to view the aft end of the vessel during standard operations. To attain this, a second, smaller helm is included at the aft end of the wheelhouse deck to allow for a complete line of sight on the mission end of the vessel during standard operations. I will now pass it off to Jack to talk about the vessel's mission systems.
Thank you, Corbin. 2 of our main mission systems are found on the aft deck. We have our crane and our walk-to-work system. While we have not specified a model of marine crane, the crane must have a 15-meter radius and a greatest safe working load of 10 metric tons. The walk-to-work system selected is by Safeway. It is the Seagull model with a maximum radius of 28 meters, a 1.1 meter wide and closed hallway for all weather conditions, and both systems are compensated for heave of up to 3.5 meters, taking positioning data from the dynamic positioning system. Moving to the main deck, the diameter of the crane is shown below on the starboard side, and the diameter of the walk-to-work system at its minimum extent of 18 meters is shown above on the port side. There is a footprint for 4 20-foot equivalent units on the aft deck right in front of the mooring station, and there is additional space above the deck warehouse for 4 more containers. Although space for a total of 8 TEUs was specified, 40-foot containers could also be placed atop the deck warehouse to accommodate any changes in mission without even encroaching on the basketball court. The daughter craft is shown on the port side. It may be lowered by davit, but is usually stowed inboard during transit as shown. Although we were not tasked with selecting a daughter craft, this boat was chosen as a sample crew transfer boat. The height of the foredeck above the waterline was used to design a ramp which can be lowered continuously for stepless crew boarding, especially in choppy conditions. The helideck is located above the wheelhouse to accommodate the demanding visibility and turbulence conditions for offshore helicopters, which are imposed by the Helicopter Safety Advisory Commission. While it is not the largest helideck in the business, it is large enough to accommodate common offshore helicopters, such as the Leonardo AW139, which is pictured, and the Sikorsky S92. Finally, we can accommodate crew transfer movements with the crew transfer basket. This is a reasonably simple method of crew transport, which uses a circular rig suspended from a crane to transport personnel and/or tools and personal effects. It is rendered ineffective in strong winds, but it can be useful for moving offshore technicians by crane in the event that our walk-to-work system is inoperable. Moving on to our weights and centers. Here we see the summary of the lightship weights and centers given. The SWIBIS structure, as we've already heard, allows for a methodical breakdown of ship weights, and multiple MERIT publications allowed us to take real-world data in the same form to inform our weights and centers estimations. Although categories were given, all categories were given significant acquisition margins to making the current estimate quite conservative in view of possible future additions. Notably, the margin on the whole structure is even greater than the other categories to account for additional structure associated with the deep framing process related to tonnage, which you'll hear more about later. Here are the basic weights and centers for the vessel in the lightship condition. The vertical center of gravity is indicated by the lower red crosshair, and the transverse metacenter is given by the blue crosshair. Loading conditions are prepared for the lightship, the full load departure, and the full load arrival conditions. In the full load departure condition, we see that the vertical center of gravity is lowered as all of the tanks are filled with fuel oil and fresh water. There is a slight trim by the stern, but there is zero heel, and of course there's plenty of transverse and longitudinal metacentric height, or GM. The vertical center of gravity and transverse metacenter do not vary much between the full load departure and arrival conditions. The VCG rises when much of the fuel and fresh water have been expended, but there is more than enough transverse metacentric height to satisfy regulatory requirements, safety requirements, and crew comfort. Finally, to ensure regulatory compliance, the dynamic stability of the vessel was assessed by creating GZ curves for the three principal loading conditions. An analysis of downflooding was also conducted, and the angle of first downflooding was shown to be well beyond the expected range of heel angles, so it was not considered when assessing stability criteria. These analyses showed compliance with all of the IMO's intact stability code. Next, I will welcome Andrew to talk about the structure.
Thank you, Jack. In order for our ship to safely function in dynamic environments, it has to be strong enough to withstand a wide range of loads. To accomplish this, we selected steel as the material for our superstructure. The first reason we chose this is because of our parametric analysis, where every single similar ship also had steel as its superstructure. We thought this was a pretty good indicator, and also steel is ductile, has a high strength to weight ratio, and is relatively inexpensive. We chose to frame our ship longitudinally because of two reasons. The first is also because of our parametric analysis, where the majority of similar ships were also longitudinally framed. The second reason is because of the loads that we anticipated. Our ship will encounter heavy wave loads due to its operating offshore along the East Coast, which is a summer zone. Wind farms are actually built in areas of high wind, which means that our ship will have to deal with more severe weather. We also have heavy point loads aft in the crane, walk-to-work, and cargo. The engines are amidships, the hotel is fore, and all of this creates a large longitudinal bending moment. We made sure our vessel complied with Bureau Veritas rules and used NR 467 to calculate the minimum required values for section modulus, shell plating thickness, and deck plating thickness. After selecting our thicknesses, section modulus for our midship was calculated and found to pass requirements. Working for offshore wind, it's important that our vessel is sustainable. This means having a reduced impact compared with similar sized vessels, being capable of zero fossil fuels mode for 24 hours, and having a 25% overall reduction in fossil fuel usage. We're accomplishing this using biodiesel and dual fuel methanol capable generators. And this vessel is intended to separately bunker both standard MDO and pure biodiesel B100. This allows for the blending of fuel on board to achieve different emissions profiles depending on operating location and potential regulations. Our vessel must have redundancy for our mission. To ensure adequate power is always available, an EPLA was conducted. The cases analyzed in our EPLA were cruising, mission operation, and an onboard emergency scenario. For the two standard operating conditions, the required power is less than half of the installed power, meaning only 2 generators are needed most of the time. For emergency, the EDG alone can supply enough power, meaning adequate power will be available even if all 4 main generators are compromised. A conceptual electrical distribution system was also created for our vessel. The system operates at 2 voltages, 480 volts and 120 volts. All the machinery runs at 480 volts, and the 120 volt panels are included for smaller loads like lighting and navigation equipment. This system layout is very standard, consisting of several discrete panels for each level and area of the vessel. In order to maintain a stable platform, our vessel must meet dynamic positioning Class 2 requirements. This means we must be able to automatically and manually position the vessel while compensating for wave motions without losing position because of any single fault. In order to ensure the Class 2 requirements are met, the ship is equipped with adaptive power management and also Voith-Schneider propulsion. Our ship has 2 Voith stern thrusters, 2 Voith-Schneider propellers, and 1 retractable bow thruster. The real advantage of Voith-Schneider propulsors as the main propulsion is their ability to compensate in surge, sway, roll, and pitch, in addition to propulsion in any of those directions. You can see the location of our propulsion systems on our ship here. We have 2 aft VSPs, 2 forward VITs, and 1 retractable azimuthing VIP. Now, I'll pass it off to Malay Metz to go over regulatory compliance.
Thank you, Andrew. So one of our most important requirements was tonnage. And for this vessel, we need to be under 500 gross tons. Tonnage is a measurement of volume, and there are certain exemptions that can be made, so subtracting certain spaces from that volume using the Marine Safety Center technical note on tonnage technical policy. It details the exemptions that can be made from the volume. We use this as well as the help of our mentor, Phil Essex, to design around the tonnage. There are certain design choices that can be made in order to lower the measured tonnage. For example, to lower the tonnage layout, we deep framed all of our tanks, which lowered the tonnage of the below deck spaces, and the superstructure was designed around tonnage so that we could exempt the entire superstructure. We did this by having tonnage openings on every deck of the superstructure, as well as continuous hallways through the superstructure to exempt them. For Jones Act compliance, we must have the ship be U.S. built, owned, registered, and be crewed by 75% U.S. citizens. To meet our U.S. requirements, we took note of the location of the manufacturer's U.S. headquarters and made sure that all of our machinery had U.S. headquarters. For statutory compliance, the vessel was required to meet the 46 CFR as well as the IMO Intact Stability Code. The tonnage dictates the subchapter of the 46 CFR that is to be used, which is one of the reasons why the tonnage measurement is so important. We created a designated requirements compliance matrix to aid in keeping track of each requirement, where it came from, and whether we were fully compliant or not yet at that time. The statutory class and design requirements influence almost every aspect of the vessel's design. There are requirements on everything from the size of the staterooms to the placement of the bulkheads, engine and propulsion to safety and equipment. Some notable requirements are the transverse metacentric height requirement, the requirements on locations of watertight bulkheads, and the size of our heli deck. Some steps we took to meet requirements were including space for fire extinguishers and escapes, adding fire pumps, and adding fire lockers. For this design, we used the Bureau Veritas Class Society. We used the rules for classification of steel ships, as well as the specific rules for offshore units. Some of these requirements did overlap with the IMO, and Bureau Veritas has requirements for crew and passenger safety, propulsion and redundancy, stability and arrangements, and almost every aspect of the ship. In conclusion, this offshore wind support vessel is designed to meet the demanding requirements of a year-round operation in the offshore environment, as well as operating up to 100 miles offshore with a 30-day endurance. Our vessel is versatile enough to be used in other industries should it need to be, and this is achieved with our mission systems, which include the walk-to-work system that includes a crane, an additional crane, ample meeting and accommodation space, including extra accommodation space, 10 berths over what we were required, as well as stepless helm, stepless landing, and second helm. Our vessel provides a safe, efficient, and comfortable platform for offshore wind operations, and it is designed to enhance operational reliability, worker safety, and mission efficiency to support the offshore wind industry on the East Coast. Thank you so much for attending our presentation, and we look forward to any questions.
Very much. I have a somewhat theoretical question. So I understand the 500 gross tonnage limit was really essential to the prompt, probably because it unlocks some additional requirements that need to be met to the vessel. While you were in the process of reducing the gross tonnage, was there anything that you removed that you would rather leave in?
I can't think of anything specific, but most of it was just rearranging the spaces in the superstructure. So moving around certain rooms. We didn't get rid of anything, but we did change the locations and shapes a little bit. Thank you.
We had to cut down on our engine room space a lot too. Originally, the engine room was a lot larger, which is preferred for the crew, obviously. And shrinking that down to a much less manageable size is not preferred.
And I'll add the deep framing also is not super ideal in the engine room. So that's a little bit of a downside as well. Thank you.
Thank you.
Obviously, designing a vessel for optimum design and doing an optimum tonnage, you've learned this 2 different things. Knowing what you know now, if you were to start from scratch, what things might you consider doing differently in order to approach the tonnage parameter?
In order to approach the tonnage, so the question is, what would we do differently in order to approach the tonnage parameter from the beginning? We would definitely make a shorter vessel, as well as there's a few spaces that maybe are a little larger than they need to be. So if we were to do another iteration on the design spiral, we would look at that and maybe making some spaces smaller.
Yeah. The other adjustment would be early on, we included ships that were foreign flag that didn't meet tonnage requirements. They're generally larger on average because you want a larger ship, more space, more efficient, better in general, but US ships will be smaller. So it would have taken those out of the data set.
Also, our frame spacing, we would have chosen a different frame spacing because deep framing is every 2 frames, which we could have had be 8 feet. Yeah. Instead, we have 0.75 meter frames. So we really just added a bunch of weight in deep framing those that we didn't need to.
I think I recall you had pretty high GM in your impact condition. So would you consider shaving off some breadth as well? We
could consider lowering the beam slightly to decrease the volume inside. we can also reduce the visible area kind of to the tonnage by just making the tanks wider. We want to keep the deck area large so we can carry more cargo. So that was the main driver behind the beam being the 21-inch meters. So overall, the beam isn't really the driving factor in the tonnage we found. It's mainly just the length and the size of spaces.
And similar question, you should expect, any consideration for the walk-to-work system being out in the middle of nowhere?
Can you take a shot at that? The question.
I took a shot, but
Fair enough. Scrolling backwards to the main deck plan view, and here we see that the walk-to-work system is right at the right at the rear end of the deck warehouse, and part of the consideration for that was ergonomics, because the crew will be living in the superstructure and then making their way down to the main deck where we have the conference rooms, and so any organizing that they need for that day, they'll be able to walk through the warehouse, all of which is covered from the elements, pick up any tools or personal effects that they need to go and complete their work, and then only a brief walk outside to the walk-to-work system. And so we saw that design as being reasonably straightforward for the crew. We did certainly consider moving the walk-to-work system closer to the deck house, although we valued having open access to the deck from the house, so that especially for firefighting, in case there was anything on or around the deck, we would not have to work past the walk-to-work system, as it was right in the way of the firefighting locker. And this walk-to-work system also essentially functions as an elevator. And so if it was down right in front of the deck house, then that would be very challenging to get crew and also material moving around that. I hope that answers your question.
it does, thank you. Just as a follow-on, since we're here on the main deck, I'm pointing a bit, but if I see that's the crew duty mess and officer duty mess, any consideration to the size of those spaces relative to the two changing rooms forward then? How many people are you expecting to feed at once?
Yeah, the duty mess on the main deck isn't the main eating space. That's just like a quick snack between work, like coffee, stuff like that. It's not the main like mess space on the deck above. It's probably.
Great, thank you.
Get there.
Yeah, I had a question. Can you go to that midship? It looked like the inner bottom is discontinuous. On that, it looks like that might be in way of the main engines. Was the inner bottom reduced in order to have the overhead height for the main engines?
Yes.
Okay, yeah. So just again for future, the localized foundation structure on the engines likely going to need to be increased to support the weight of the engine. So it just might be something worth considering at a lot of times that you're needing to have that open deck above the engine room. Might need to take the space from above that.
Thank you.
Definitely on the next iteration, you would account for that. But you.
I noticed you mentioned you use modular berthing. Cool idea, and you're glad you thought about electrical power. How about water, wastewater? Probably only impacting your pickup.
We did not consider so the question was whether in the event of adding a 40-foot equivalent unit modular housing on top of the deck warehouse, we have the electrical power for those, but we had not included anything for fresh water and wastewater, which would also be needed if people are going to live there, especially long term. It's a great question. We did not consider first and foremost for that modular housing addition. The crew, as given in the specification, was 60, and I believe we actually have closer to 70, berths for closer to 70. And so anything additional would require an engineering rework of at least those habitation systems.
Questions coming from online. Can you please describe the machinery and the role prevention?
Sure, yeah. The machinery there was kind of vestigial space, more of extra machinery space, because that was put in when it was originally a tank, then it became cruise in general. There's no current like additional machinery needed because both repulsors on their own have roll compensation as part of them. So right now it's kind of vestigial. It should be labeled unassigned. That's the main issue there.
Yeah, we actually looked into getting rid of that room too, for tonnage requirements. And when we learned about the roll stabilization capabilities of the moisture propulsion, I was looking at an article on the North Sea Giant, which is a similar vessel but longer in length, and it has 5 ESPs for propulsion, and it had very good dynamic stability.
Great. Can you comment on the position of the control room on the outside of the stack? The comment you made suggests there might be a tension in order for it to flip from accumulator over windows.
It's you can view it there. Yeah, I think. Yeah, so the question was with the regards to the aft helm for view during operations. Are there issues with soot accumulation? We didn't consider that. It's a very good consideration. I think definitely some kind of redesign of the stack to ensure that the soot is redirected away from that second helm to prevent the window from being covered, because that makes them less useful for sure.
I'll add to that. We did consider moving the exhaust so that it wouldn't have to be, the extra helm wouldn't have to be on the back, but we had already had the exhaust in place before we added that extra helm. So it would have meant changing a lot of the design. But definitely on the next design iteration, that's something we would do.
Did you consider a battery solution with charging from the wind farm to meet the 24-hour requirement?
Do we consider batteries from wind farm charging as a means of meeting 24 hours without fossil fuels? We did not currently, but that is a good idea. So I'm not looking at that, search about that open space.
And then the last question that I have here right now is, what is the damage stability standard that you use?
So for the damage stability, the question was, what kind of damage stability standard did we use? We used one compartment. The reason it's not up in this presentation is because we need to do a slight redesign. One of the sections isn't actually fully compliant yet, and we didn't quite have time to redesign all the bulkheads. So that'll definitely be reconsidered within the next design spiral, next iteration of the design spiral.
Okay. Thank you very much.